is the one that you hear spoken, like 12% compounded monthly. Okay? And that whole sentence is the nominal rate, 12% compounded monthly. Now, you break down 12% and note it as compounded monthly, but the thing that you're interested in is the second, or the bottom one, which is the periodic rate, which is the nominal rate, R, divided by the number of compounding periods, which we have used K to represent. So that is our periodic rate. The nominal rate divided by the number of compounding periods. So it's 12% compounded monthly. The periodic rate would be 0.12 divided by 12. So R over K equals I. And that also means that I times K equals R. This is nominal. This is periodic. This is number of compounding periods in a year. Not to be confused with N, because what is N? That's the number of compounding periods over the lifetime of the obligation. That's N. Right, so let's keep all our letters sorted out. Now the other thing I taught you about was effective rate. And the effective rate is an equivalent annual rate for whatever the interest rate is you happen to be considering. The reason we give it is so that we can make a true comparison between these rates. So if I ask you which is better, 12.3% compounded monthly or 12.4% compounded quarterly, would you know which is better? You wouldn't, okay? You'd have to do some calculations first. You'd have to find the effective rate. So the effective rate for each of them is going to be 1 plus R over K to the K power minus 1. So it's 1 plus the nominal rate divided by the number of compounding periods raised to that same number minus 1. Why raise it to that? Because we're looking at 1 year. So that's how many you're going to have in a year. And that'll give you the effective rate. So we do it for the one, we do it for the other, and the one that comes up with the best answer, that's the one that we want. So we said 7.3 monthly versus 7.4 quarterly, right? So we do our effective rate here, which would be 1 plus 0.073 over 12 raised to the 12 minus 1. And this one here would be 1 plus 0.074 over 4 raised to the 4th power minus 1. The question is, which is best? So now we have something to do with our calculator. We'll do the first one here, 0.073, enter, 12, divided 1 plus 12 over here, y to the x, 1 minus, and we're going to do that, we're going to express it in a percentage, so we're going to say 100 times. That's 7.55. We're going to store it in 0. Okay? Now the other one was 7.4%, right? So 0.074, enter, 4 divided, 1 plus 4 y to the x, 1 minus, and then 100 times. Which is better? 7.3 monthly or 7.4 quarterly?
7.4.
It's a little bit, not that much, but a little bit. Okay, so that's 7.61. Here's the one, we're going to recall the other one. 7.55. So you get 0.05%. Okay, small, but the one is better than the other. So that's what we do with our effective rate. And then we already did this at the end of last class. When you're doing interest rate equivalencies, you put them on both sides, and then you pick a common period. So on the one side, it might be semi-annually, so it'll be 1 plus R over 2. On the other side, it might be quarterly. So in this example, it's 1 plus 0.10, 10% divided by 4, because it's quarterly. And the common period might be 6 months. So there'd be 2 quarters in that. So we raise that to the second power. On the other side, there's only one 6-month period. We raise it to the first power. We solve the equation and we find out that 10% compounded quarterly is exactly equivalent to 10.125% compounded semi-annually. And so we really wouldn't care if we got either one of those. They're exactly the same. They will give us the exact same result. Now, that brings us up to what we have to do today, which is finding time. All right? We had our equation that we were using for compound interest, S equals P times 1 plus I to the n. Well, we want to find time, we want to solve for n. Well, the first thing we're going to do is divide both sides by P. Okay? And that gets rid of this here. And now we got to get the n to come down to the main line of the equation. It's in the exponent. So what we're going to do then is we're going to take the log of S over P is equal to the log of 1 plus I. And now that we're using logs, it would actually be times n. The n drops down. Okay? You take the log. A log is like an anti-exponent. And now I can divide